scorpions.
Oh,
So you were spot on.
All right, we'll do a little bit of review as we wait for everybody to finish getting in and getting settled. Just a reminder, today we're going to keep going on resonance structures and get an idea of, if all of the resonance structures are equally stable, then we can assume that they're all going to contribute evenly, and that your actual electronic structure is going to look something like just the regular average of all the possibilities. Thing is, not all resonance structures are equally stable. So the most stable resonance structures are going to be the ones that contribute the most, and the ones that are a little bit less stable contribute a little bit less. So it's more like a weighted average, where the weights are based on the stability of those resonance structures. That's not what I want. All right, so we'll pick up where we left off and practicing with these. This one we've already seen, and so I note about drawing electron movement. This is going to be the same rules we have for drawing all mechanisms in this class, basically, and they're all going to go with that Born-Oppenheimer approximation, where we're going to assume that no nuclei are ever going to move. At least that's not the steps that we're going to show. So we're always going to be showing electron movement, and the way we do that is with these curved arrows. Remember back in Gen Chem, I may have mentioned that chemists get really, really picky about their arrows. Here's another case of that. If it's a curved arrow, it's showing electron movement. So you've got regular reaction arrow, you've got equilibrium reaction arrows. You've got resonance arrows, which are separate from the equilibrium reaction arrows. The double-sided arrow, you're saying it's a resonance structure. And then if it's a curved arrow, you're showing how electrons are moving. All right, so we don't consider resonance structures to be equilibrium, because really they're happening too fast for that. It's not like things are really happening back and forth. It's really both at the same time, so we use a different arrow to indicate that. And if we're showing electron movement, it's always showing where the electrons are moving, and it's always a curved arrow. Right? And when electrons move, they're always going to be moving towards something with a positive charge, or a partial positive charge, or at least a nucleus. Right? So you're always going to start your arrow with electrons and end it towards another nucleus. You're moving them to either make another bond, sometimes you're moving them to break a bond, but it's always showing the electrons moving, and it's always moving towards something, towards a nuclei, in one way or another. Towards a nucleus. I've been saying nuclei so many times that I forgot the singular. It's like data, right? Everybody know that data is plural? Anybody know the singular of data? Datum. With a UM.
Wait, what? Say that again.
A single piece of data is a datum. So, just for your own edification, so you can have a little English lesson in your OChem class. Brad.
Is there a difference between resonance and like the waves with respect to this, or is it based on that as well?
It's just like when we hybridize the orbitals, where you get the constructive and destructive interference of the possibilities. And the more overlap, the more constructive interference you get, the more stability you're gaining. It's the same thing here. We're looking at the different possibilities overlapping together. And that's what gives you that's what takes a hybridized orbital, or in this case, a pi orbital, and turns it into something bigger. Okay, so for this first one, we already showed this one once, and the way we show the arrows moving, or the electrons moving, is one of these bonds. You don't really differentiate between which of these two is the pi bond when we're drawing skeletal structure. So pick one and draw it moving towards the positive charge, which gives us a new resonance structure. Looks like this. We broke a pi bond to the carbon on the left-hand side, moved those electrons over to what the carbon that had a positive charge. The positive charge means it has an empty spot there, right? When you've got a carbocation, that means it's got a partially empty orbital. And that, in doing so, we broke up the full octet for the carbon on the left. Right, and so remember, just to go back for 1 second, if you did it right, your net charge doesn't change. Your total number of electrons doesn't change. So that's your way of checking whether you did something right, is no sigma bonds broke, net charge doesn't change, and we didn't draw something with 5 bonds or with 10 pairs or 10 electrons. So the second one here looks really similar on the surface, except it's if we have a negative charge on the carbon on the right-hand side. It's a negative charge on a carbon, that means it's a lone pair, actually. Right, where you have a carbon that looks more like a nitrogen, where it's got 3 bonds and 1 lone pair. Because that would be the 5 electrons, right, which is 1 more than it has on the periodic table. So you're not going to be moving this pi bond towards the negative charge, which kind of fits along with our rules for electrons are all negative, they push away other electrons, right? You also can't move it that way because it's already got a full octet. So if you have a negative charge, the negative charge is going to be moving towards something else. So you can only move 1 bond at a time. You can't just leave it like that because that would give this carbon too many bonds, right? This carbon already had a full valence. So we need to make room for it by moving that pi bond over. So the net result is that we wind up, all the carbons stay where they are. When you're drawing a resonance structure, since we're not breaking any sigma bonds, we're not moving any atoms, we can always start by just redrawing the sigma bonds. We added a pi bond here between the right and the middle carbon, and now we've got an extra pair of electrons on the left. Right, so similar in that it looks like the net result is that the charge jumped 2 carbons, but the arrows moved in the opposite direction, because remember the arrows are showing the electron movement. And too many electrons moves in the opposite direction as too few electrons. Here we have, that's an ester, is that functional group. Again, I know the arrows are already drawn here, but just so you can see why the arrows are drawn where they are, because that's our next step, is you guys draw the arrows yourself. We have some lone pairs on these oxygens, right? And get a lone pair next to a carbon with a pi bond, then we can have some resonance. And that's basically, it's very similar to what we just did here, except it's an oxygen lone pair instead of a negative charge from a carbon. this bottom oxygen's lone pair can contribute a resonance structure by moving over and towards this carbon over here. And well, why would we do that? That seems like everything's already perfectly stable the way it is. It's not like this one has any charges on it, right? But you've got partial charges, right? Think about your polarity. If you've got a partial positive here and a partial negative here because polar bonds, well, I mean, that's not the same as a full vacancy. We still have to make room for electrons, but that's still going to be attractive to a lone pair that's right next to it. So we wind up with one of those lone pairs moving over. But we have to make room for it. So this carbon takes the pi bond electrons. And our resonance structure then is going to look like, well, we made a new pi bond that's between the carbon here and the oxygen that's in the middle of this carbon chain. And to do that, we had to move a pair of electrons up. So we wind up with an oxygen with 3 lone pairs at the top. And we wind up with an oxygen with only 1 lone pair at the bottom. Those have charges though now, right? Oxygen with only 1 bond has too many electrons. An oxygen with 3 bonds has too few electrons. And they're not a partial charge anymore. It's a full positive and a full negative charge, which still follows our rules for resonance structures, right? Because the net charge still adds up to 0. It was neutral over here. The whole molecule is still neutral here. We just have some individual charges based on how we move the electrons around. Would there be really any substantial difference if we switched what those atoms were? The arrows and positioning and everything still looks the same for this one, right? It's going to look a little bit different. I draw the carbon on the nitrogen going the other direction for the sake of showing this. And if you have a negative charge on a carbon, you have to have a lone pair on it. And usually, at least in our textbook, that lone pair is drawn like a regular lone pair. And then the negative charge is drawn next to it as well. That certainly makes it easier to show these resonance arrows when you have your lone pair explicitly drawn, so you can draw the arrow starting there, right? So, extra pair of electrons on a carbon, it can share those. But we can't just move them over because that would give us 10 electrons around this carbon. So we have to make room for it. Which is going to give us, we're going to break the pi bond to the nitrogen, make a pi bond to the carbon that has the lone pair. We didn't move this carbon off to the side here. We just now have a nitrogen with 2 lone pairs and 2 bonds instead of 3 bonds. And so that's a nitrogen who controls 6 electrons, 5 electrons on the periodic table, so that's where our negative charge went. Right?
So that nitrogen initially did have 1 lone pair, now it has 2.
Exactly. So I didn't draw it here, but 1, 2, 3 bonds, but that still has to have 8 electrons, so there was a lone pair there as well. one more note about being picky about arrows. These curved arrows, always make sure you draw them, they say double barbed, means like a full arrow. Don't do it like an equilibrium arrow with a single barb. If you draw a curved arrow like that, that means that only one of the two electrons moved. So when we get to free radical reactions, that's how we can show that, for instance, if you have, let's look at, we can just use chlorine. When you shine the right light on the right wavelength of light on chlorine, you can actually match the energy between this bond and its antibonding orbital, which causes the bond to just disassociate. And so the way we would show that mechanistically is like that. Still a curved arrow, but the fact that we only use one barb on each of these says that this electron goes this way and that electron goes that way. That's going to be the exception. For the most part, we're going to be dealing with pairs of electrons. So usually you want your arrows to look like this. I'm all for creative expression and you finding ways of drawing things that works for you, but not when it comes to how you draw your arrows. Incidentally, that's also why iodine and hydrogen peroxide are both sold in opaque brown bottles. Because otherwise visible and UV light will break those bonds and you wind up with a big mess of stuff that's not iodine or hydrogen peroxide anymore. And it's also why hydrogen peroxide will go bad if you don't have the lid on tight. Not because of light in that case, it's just because if you let oxygen in it, oxygen will react with hydrogen peroxide and water. All right, so let's have you guys practice for a few minutes. There's three possible compounds. Start with A. Think about where the lone pairs are and where there's empty spots or where there's extra electrons. And see if you can draw some different resonance structures. And to remember, don't break any sigma bonds. Your overall charge still has to add up to the same charge at the end. right? So for this first one, and then I'll give you another minute to do B before we go over it. We've got two atoms with a lone pair next to a carbon that has a vacancy, right? If you have a carbon that has a vacancy next to a lone pair, that lone pair can jump into that empty spot. Right, and then that acts to fill that carbon's valence now. So one possibility would look like this. We only need one arrow for this case, so we don't need to make room for this pair of electrons. There's already room.
So you don't need to draw an arrow that shows that the charge moves to the other atom.
You don't draw an arrow showing the charge moves. You draw the arrows to show that the electrons move, and then the charge is what the result is. So the electrons move over. So we now have a pi bond there. We draw the nitrogen lone pair moving over. Does the nitrogen have a lone pair anymore? So now the nitrogen has 4 bonds, right? Still has a full valence, but 4 bonds instead of 3 with a lone pair means that's where our charge is now. Because the nitrogen only controls 4, and on the periodic table it has 5. There's nothing that says that it has to be the nitrogen. The oxygen has lone pairs too, right? If the oxygen moves its lone pairs over instead, you make a carbon-oxygen double bond. And now the oxygen's got 3 instead of 2. So now the positive charge is on the oxygen. Of these 3 possibilities, which is the most stable? These are not symmetrical at all, right? So there should be some difference in the stability. Got a positive charge on a carbon, positive charge on a nitrogen, or a positive charge on an oxygen?
Let's say positive charge on the oxygen.
Why?
Oxygen's really electronegative.
So
It's
it's-
probably more likely to happen.
So if it's really electronegative, is it good at sharing or bad at sharing?
Yeah.
So right reasoning, but wrong result. So if it's not the oxygen having the positive charge,
Considering the electronegativity only, say positive charge on the carbon.
if you only look at the electronegativity, you would think this one. But what's the other piece of this? What's the most important thing with Lewis dot structures? Is our first rule for if we did it right. Full valence. The carbon doesn't have a full valence here. So, actually, the first rule of Lewis dot structures is don't add or subtract electrons, right? And assuming we can all count the number of electrons and not lose any electrons along the way. The next rule was make sure everything has a full valence. And then lastly, once everything has a full valence, we worry about where do we put a charge. And usually we would want to put a charge, a negative charge on the more electronegative element and a positive charge on the less electronegative elements. But that's our last consideration. Our first consideration is everything has to have a full valence, and the carbon doesn't here. So this is actually our most stable structure here, because everything has a full valence. There's a positive charge, but it's on a nitrogen, compared to here, where everything has a full valence, but the positive charge is on the oxygen. These are both close to the same stability. The nitrogen and oxygen are both electronegative. Everything has a full valence for both of these. This one's going to be a little bit more stable than this one. And they're both going to be more stable than this one. This is going to be our least stable. All right, take a few minutes and try B. Just like the last one. What's the first thing that's going to happen? What does this positive charge tell us? There's space. You've got a positive charge on the carbon, you've got space, and you've got electrons next to it. It's not lone pair electrons this time, it's pi bond electrons. Same principle, right? Pi bonds and lone pairs can both move into an empty spot. So our first resonance structure, you do that, and then what happens to this carbon? It's positive now, right? We stole a pair of electrons from it. Are there any other resonance structures? What do we do? Yeah, instead of starting from here, we can start from this one. Now we've got a positive charge next to a pi bond and also next to lone pairs. Well, if we take the electrons from the pi bond and move them back over there, we're just going backwards, right? But if we go the other direction, and move one of these lone pairs over to the positive charge, we didn't touch that pi bond this time, right? So it stays where it was. We added a pi bond between the oxygen and the carbon. And now the oxygen's got 3 bonds, so it's got a positive charge. The other lone pair is still there. Are there any more? Not really. We had 1 pi bond and 1 oxygen with lone pairs to work with, right? All these CH3s at the end, those are all sp3 carbons, right? All sigma bonds. There's nothing we can do with those when it comes to resonance. And of these, which is the most stable? Only one has all the valences filled, right? Even though it puts a positive charge on an oxygen, everything has a full valence at least. And then we'll get into rules for ranking incomplete valences in a little bit. But in general, it's going to come down to what has the most electron density around it. And we're going to see that tertiary carbons, so the tertiary carbons that has 3 other carbons around it, are going to be more stable with a positive charge than secondary carbon, which is more stable than a primary carbocation. All of which are more stable than a methyl carbocation, which is just a single carbon by itself. But I'll repeat all of that when we get closer to it. Questions on these two? OChem's full of cases, even more so than Gen Chem, where it's, well, yeah, it's really easy when somebody's up in front of the class doing it on the board. It all makes total sense. But when I give you a blank piece of paper, it's really hard to do it. So take your blank piece of paper and try on C.
For that last one, which case would be the more stable one?
The one that I just erased, because this is the one where everything has a full valence, even if the oxygen does have a positive. just as I think there should be 3 additional resonance structures in addition to the one we start with. And you can always start by just putting all the atoms back where they go and drawing all the sigma bonds, because we're never breaking those with a resonance structure.
So how can you tell right off the bat that there's going to be 3 resonance structures? Or is that just like practice, like you?
It's practice a little bit. And even it's just a reminder, this is a little bit like the term isotope, right? The word isotope, it tends to get used to mean things that are different from the average, but the average is still an isotope, right? Carbon-12 is still an isotope of carbon. This might be where we're starting, but this is still a resonance structure too. You're starting from 1, and there's 3 additional resonance structures. Just to be a little nitpicky with the way you have phrased that.
Yeah.
You can have an idea if all of these double bonds are alternating, and the closest one is only 1 carbon away here. We can have idea that all 3 of these double bonds can participate in the resonance. They're all what we call conjugated. And so if there's 3 double bonds that are conjugated, there's probably 3 other ways that we can arrange them. That won't always be the case, especially if one of them is isolated, for instance. If this one wasn't there, it doesn't matter that we have a pi bond here. There's no way for this pi bond to get over to this area because you've got sp3 carbons in the way. And sp3 carbons can't participate in resonance. So part of it is just getting used to it and sort of developing chemical intuition. Part of it is because I just went through in my head and said 1, 2, 3. And kind of did them mentally before I drew the structures. The first one looks very similar, right? We've seen that a lot. Empty spot next to a pi bond, move the pi bond over. Which means now we've got a pi bond here and a positive charge here. We didn't touch these 2 yet. Now we've got a positive charge next to a different pi bond. Now that pi bond didn't move. We moved this pi bond up 1 spot. Excuse me. So then last but not least, our last pi bond that hasn't participated yet, then get involved and so that it can't resonate to this top carbon because it's sp3, right? This carbon doesn't have a lone pair or a pi bond that it can contribute. And so it seems like it's moving its way all the way around the structure, but because we've got this one sp3 carbon in the ring structure, that sp3 carbon is going to stop everything dead. And same with these CH3s at the end. They can't do anything because they're sp3 carbons. If we were ever drawing a mechanism where we only specifically cared about maybe this one and this resonance structure, because maybe this first resonance structure is where we had a leaving group leave and take its electrons with it. So maybe we started here and we're specifically talking about a product that we get that comes from this resonance structure. We might not care about drawing these other ones. And you can actually draw all of these arrows at the same time to get all the way from this resonance structure to that resonance structure without bothering to draw the ones in between. But we'll get there down the road. If you have more than one resonance structure for now, draw them all, because it's each individually is a lot easier to draw then, right? Yeah.
Is there different names for like the different resonance structures?
That's a good question. Not really. Unless if you were writing a paper or something where you were talking about different resonance structures specifically, you might go through with this molecule and say this is A, B, C, and D, for the sake of in your paper saying resonance structure A or resonance structure B. But we would not name them differently as far as nomenclature goes. Brett?
Now, are these all happening pretty much simultaneously?
Right. So remember I showed you that electron density of benzene, right? That had that where the partial positives and negatives were. If we looked at the electron density map for this molecule, we would see 4 different places that had a partial positive. You're going to have a partial positive here, and here, and here, and here, all simultaneously. It's not a full partial positive charge at any of those points. It's going to be a partial positive charge at all of those points at the same time. So when we get into mechanisms and we have the next step from here, positive charges are not all that stable, right? Because, especially on a carbon, because now that's incomplete valence. The next step is almost always something that has a negative charge comes in and attaches to a positive charge. It shares its electrons. So that can be a lot of different things, but say for instance it was a hydroxide, an OH minus. That hydroxide that has extra electrons is going to be attracted to all 4 of the carbons that have a positive charge. You're going to get a mixture of products. You're going to get one product where the OH comes in and attaches there, a different product where your OH attaches here, or here, or here. So yes, absolutely, all of them are happening at the same time. And we're going to get a mixture of all the possible products. And generally speaking, what they call these statistical amounts, based on how stable these different resonance structures are, the most stable resonance structure is going to have the greatest chance. It's going to have the most positive charge, so it's going to have the most attractive force to the oxygen. But you're going to get a mixture of all 4 really. OChem is really why I really like that description in Interstellar of Murphy's Law. Okay? It's not everything that can go wrong will go wrong, it's everything that can happen does happen. And nowhere is that more evident than when you're trying to predict just how many and in what ratio of products you're going to get for an OChem reaction. Which is why purification winds up being such a big deal in OChem. Because we might only care about one of the possible products and the rest of them are trash. So then we have to figure out a way to get our one product and separate it from the other 3 that we don't want. All right. So let's talk about some patterns and kind of develop some more vocabulary. We've already noticed that there's certain patterns, like if you have a positive charge next to pi bonds, that's always going to give us the same sort of resonance structure, even if the rest of the molecule is a little bit different looking. And so one example is if you have a lone pair adjacent to a pi bond. And when you're adjacent to a pi bond, that's in the position that we call the allylic position. Allylic specifically means one bond away from a pi bond. So regardless of what we're talking about, this position and that position are both allylic. Really 4 L's or is it only 3? Only 3 guys. So anytime you have a lone pair in an allylic position or a positive charge in an allylic position, you're going to have some resonance that can happen. What is the resonance structure going to look like if you've got a lone pair? We don't have any vacancies that the pi bond is moving into, but what do we have instead? Partial positive. Yeah, partial negative here, partial positive on the carbon, right? Just by virtue of electronegativity, everything's got a full valence. So we might not expect it to be all that stable, but we can certainly draw a resonance structure where we wind up moving a lone pair over to make a pi bond, and that leaves us with a carbon that has a negative charge. All right, so then our resonance structure would look like and we didn't move any of the hydrogens, any of the sigma bonds. So we wind up with an oxygen with a positive charge and a carbon with a negative charge. Everything still has a full valence, so with respect to that, they're going to be close to the same stability, but out of these, which would we expect to be more stable? Why?
Because oxygen has a full valence.
It still has a full valence here. It's because remember we just moved it still has that other lone pair here. And when we move the pi bond over, this carbon has a lone pair which gives it a negative charge. So it's not that it doesn't have a complete valence, but it does have a positive charge. And a positive charge on an electronegative element generally less stable than not. And remember, it was sort of the third level of things we considered. When you first learned Lewis dot structures, it was make sure you use the right number of electrons, make sure everything has a full valence, and then it was keep everything's formal charge as close to zero as possible. And we had everything had a formal charge of zero up here, right? We introduced charges. Even if they still add up to zero, we still have formal charges like right here, right? So this is going to be less stable than this. And a lot of times it's because we wind up putting a positive charge on something that's electronegative if we do that. The other term that gets used along with allylic is if you have a carbon-carbon double bond at the end of a carbon chain. That's what's referred to as a vinyl group, or vinylic is the adjective, which sounds like it's tasty, like vanilla, but it's vinylic like vinyl. So not so tasty. It's actually, and that's where a lot of stuff that we hear, that's where vinyl actually comes from. It's a polymer that you make from a bunch of vinyl groups reacting together. And that's also where PVC comes from. What does PVC stand for? Anybody know?
Chloride.
Polyvinyl chloride. Yeah, if you take a bunch of vinyl groups that have a chlorine attached to them, and you let them all react together, you get this nice, really durable polymer called PVC. Allylic doesn't show up in names as much because it's usually for describing a specific part of the molecule as opposed to the molecule itself, the way we see with vinyl groups. All right, so we have a bunch of allylic lone pairs. Lone pairs adjacent to a pi bond. So in each of these cases, we don't have empty space, we have extra electrons. So you're going to have to draw at least 2 arrows for each of these, right? So you got to make room as well. So give these a go, and we'll go through them. Remember, if you do it right, your charges still have to add up to what you started with. If you start with a neutral compound, you might be making a positive and a negative. And a reminder that with these, if it's not a positive charge, we're going to be pushing electrons out of the way instead of pulling electrons into an empty spot. So we're going to make room for them. Okay?
For A, that oxygen, the one on top, it did have a lone pair to start, correct?
It did. I had 2 lone pairs to start. So that's why it goes from 2 to 3 lone pairs. And we'll see that a lot with negative charges. Nothing can have a negative charge without already having a lone pair, right? It's not actually nothing on the periodic table the way our rules work. You can't have a negative charge without a lone pair. If there's a negative charge, by definition, as far as I can tell, you're going to have a lone pair. So a lot of times, especially with carbons, we won't necessarily explicitly draw the negative charge and the lone pair. We'll just draw the negative charge and treat it like we're moving a lone pair. But to be as accurate as possible, I should have done it like that with the negative charge and shown the lone pair moving. Is there really any difference between A and C? It's a carbon instead of an oxygen, but it's still pi bond in the same position relative to a negative charge, right? Or next to a lone pair. So instead of being an oxygen with 2 lone pairs, it would have been a carbon with 2 hydrogens. And for a lot of these other atoms that do have lone pairs, when they're neutral, you would want to draw the lone pairs, at least the ones that you're going to show moving. And same thing, lone pair moves over to the sp2 carbon that it's adjacent to, and then you have to make room for it. And now all of a sudden we've got a carbon with a negative charge in a lone pair. An oxygen with 1 lone pair, which gives it a positive charge. So the same basic patterns happen all the time. The specifics look a little different. You have to pay attention to what's charged and what it looks like. It might affect what it looks like in terms of, well, this carbon has 1 lone pair and 2 hydrogens instead of an oxygen that had 3 lone pairs. But electronically, it looks really similar, right? As far as where the bonds are to the heavy atoms and where the lone pairs and pi bonds are. Right, so our book actually calls out sort of 5 really, really common patterns that we'll go over in a minute, because this is as good a time as any to take a break. So come back to 5 after.
Yeah, take a break already, buddy.
It's too early, there's nothing to go do tomorrow.
How you gonna grow up and be tall and dumb like me if you don't take a break, man? You know, I wish there was an exit right here so we could just, you know, the whole outdoor thing is a little tough.
It is tough.
Me too, I work in coffee, like, I get snickers, and then I'm like, no, I should wait for another coffee, and my coffee is like, hold on to. It works.
Yeah, dude, I hopped in the car and I could see my breath and going, oh yeah. Seasons are changing. That's right. I dig it, man. It kind of makes me feel like invigorated or something. Oh, no, I'm not a fan of the warm. Yeah, I'd rather be too cold than too hot. Oh, for sure. Okay. I don't know, I like the warm. Nah. That humidity is just, puts me in bad mood. Too hot, too humid, good thing. So I have a question for you.
Okay.
Last night in geology, we were talking about crystalline structure of silica,
Mm-hmm.
and I was curious if they double bonded.
They don't typically. So because you've got oxygen, it's in the second energy level and silicon's the third. There's a mismatch in the size of the orbitals, and so it's harder to get a lot of orbital overlap, especially for those pi bonds. Sigma bonds you can still do all right because it's just direct overlap, but between that and the fact that there's such a big difference in the electronegativity, you don't see it very much. You do see something, but it's typically what we consider a defect. Did you guys use that word?
No.
So a defect in the crystal structure just means a place where it doesn't fit that repeating periodic structure. And silica being so common means that we actually have like catalogs of what the most common defects are in silica because it's everywhere. You wind up with things like,
Yeah, without like.
you know, where you've got your difference in the, you know, maybe instead of making like perfect six-sided rings when you look like down it one way, maybe you left out a couple atoms and you get this. And this is actually for graphene, so these are all carbons in this case. But it looks very similar when you have defects in silica. And so you do wind up with some weird stuff happening, maybe some pi bonds forming if you have the wrong number. There's a good example. Yeah, even still with those, most of those are not forming pi bonds. You're going to just, instead of forming, this is your most common structures when you have alternating silicons and oxygens in a roughly hexagonal structure. But if you wind up with a silicon that makes 3 bonds instead of 4, that's going to give you a defect. If you wind up with a silica that has 5 bonds instead, and that's allowed because there is an empty d orbital, and they will still all add up to the same overall formula of 2 oxygens for every 1 silicon, but that's on average, and so that's what they call amorphous, which is just totally random for the most part, or at least random enough where it's like out of every 100, maybe there's 1 defect, as opposed to crystalline silica, where you might have out of every 100 million, there's 1 defect. And that really is the only difference between crystal and glass. Amorphous silica is glass. If it's got a high degree of crystallinity, it's crystal, like Waterford crystal somewhere, that kind of thing. The only difference is how prevalent the defects are. There is also, if you're getting into crystal structures, I think it's called CHM221 3D. It's the one, yeah, it's maintained by the University of Liverpool, maybe Nottingham, somewhere over in England. But they actually have a lot of examples of good crystal structures. Like you can look at defects in ion transport, silicon sulfide. There's this titanium oxide. But it has these, and you can kind of click through them, and it builds it in 3D, and then you can kind of drag it around to see what it actually looks like. So, and then you can do things like that that show the unit cell, usually. What is that? It's been a while since I've used this, but you can see how it's got that really repetitive structure where every one of these boxes has the chloride in the middle. Okay. Anyway, yeah, so when you get into, are those, that would have been that's probably titanium in the middle. The green. Turns out studying solids is really, really complicated.
Yeah, I figured that out last night. Because it wasn't making sense to me. Because the first one we saw was Si4010, something like that. And then you just kept going down, down, and down. And I'm like, that makes no sense to me. How can you just keep going down like that without losing stuff, you know?
It's all about getting that smallest possible repetitive structure, that smallest possible repeating cube. And sometimes by rearranging things, you can get it to be really small, especially if you only have one type of atom. That's how you get to like body-centered cubic and face-centered cubic and things like that, and simple cubic if you covered in Gen Chem. But as soon as you make it a binary compound where you have two different types of ions in there that have to add up to the same ratio every time, it gets really complicated looking really fast. So the computational chemistry that I did in grad school was mostly OChem in gas phase, because that's a lot easier to study because you can actually treat it like it's isolated molecules because gases are. My buddy was studying the cathodes, I think it's the cathodes on lithium ion batteries. Which is all of a sudden, that's a surface. And the surface is even more complicated than just a crystal structure because it's a crystal structure that is only periodic in 2 dimensions. It doesn't repeat in the 3rd dimension. And so he had built these structures, these unit cells that repeated infinitely in 2 dimensions, but not in the 3rd dimension. And then use similar math and computational procedures to figure out what these lowest energy states were. It's really wild the way they use sine waves instead of just normal functions, spherical functions. They use sine waves to mimic the orbitals in that case, and it makes everything more complicated. All right. So allylic lone pair is the one we were just looking at, right? Anytime you've got a lone pair next to a pi bond, there's another way you can rearrange that. And it's always going to take 2 arrows to do that. Right? Because you've got to move the lone pair, and then you have to move the pi bond over too to make room. These carbocations are going to look really similar. There's allylic carbocation, so carbocation that's adjacent to a pi bond, or a carbocation that's adjacent to a lone pair. Technically 2 different things, but the result is it's pretty similar to draw the resonance structures for those, right? In both cases, if it's a carbocation, you're going to be moving electrons towards that empty space, towards that positive charge. This is one we haven't talked about that much yet because it's not as common as these others. It's not as stable as these others, but anytime you have a pi bond between 2 atoms, where one atom is more electronegative than the other, you actually have a resonance structure where the more electronegative element just straight up pulls the pi bond electrons over to itself. And so the result of that, you actually wind up making something that's that doesn't have a complete octet in this case. Right, so you've got 2 lone pairs here, but because it's so electronegative, you can draw a resonance structure that just looks like that. And then your product is just going to look like, remember, all your atoms stay where they are. The oxygen now has 3 lone pairs, gives it a negative charge, and carbon's just SOL. It just lost its electrons, can't really do much about it, because oxygen's a bully. Again, this happens, and this is one of the reasons why carbonyls, carbon-oxygen double bonds, are more polar than a carbon-oxygen single bond, is because you do have this resonance structure happening. And it's really happening all the time, but it's so you really do have both of these simultaneously, but it's really more of a weighted average, right? You have both of them that can be happening at the same time, but because one of them is so much less stable than where you started, not only did we add charges here, we also broke up a complete octet to do it. So it's really, if we were looking at the relative weights for how common it, I'm struggling to phrase this in a way that doesn't make you think it's just flipping back and forth. That's not really what's happening. It's both simultaneously, but we can think about it in terms of this. It's like, okay, well, 99% of the time it looks like this, and then 1% of the time it looks like that. It's not really, like, it will momentarily flash this and then back. It's really both at the same time, but it's as a weighted average. So when you take these orbitals and times them by 0.99, and take these orbitals and you multiply it by 0.01 and add them together. That's a lot less intuitive, though, than just saying that 1% of the time it looks like that. That's more accurate. But sometimes it's helpful to think about it in terms of, well, most of the time it looks like this. That's a convenient way of describing things, just like saying oxygen's a bully. Oxygen's not actually a bully, right? You guys all know that, because atoms don't have feelings.
They might.
They might. Which makes me think of that Nirvana song, "It's okay to eat fish because they don't have any feelings." It's okay to take the electrons from carbon because carbon doesn't have any feelings. All right, the last of these patterns is if you have conjugated pi bonds enclosed in a ring. So remember, conjugated just means alternating. If you have conjugated pi bonds enclosed in a ring, they can always just be sort of running in circles. I can't remember if it was my OChem professor or my biochem professor in college. They used to describe it as, it must have been Sheldon, it must have been my OChem professor. There's just something magical about 6 electrons in a ring. It's like 6 magical unicorns chasing each other in a circle forever. When you have those conjugated pi bonds in a ring, you have this resonance happening all the time, which gives you that benzene donut of electron density. The least tasty form of donut. All right, so let's see if we can recognize some of these patterns. Because sometimes you have both of them happening at the same time, 2 of them happening at the same time. So for A, try and draw, there's at least 2 resonance structures for A. 2 additional resonance structures. And for those of you like me that were not struggling to figure out what that name of that Nirvana song was, it's Something in the Way. I got it. That one. Not the Beatles, Something in the Way. Something in the way she do. Not that.
Something.
Yes. And incidentally, I just found out that that song, that Nirvana song, charted for the first time ever in 2020 because it was used as a promo in the Batman movie that came out in 2020. 30 years too late for Kurt, but hey. All right, for A, where's my big black one? It doesn't look off the bat like we have a whole lot to work with here. There's no charges. The only lone pairs already have a pi bond here, right? So it's not the lone pairs in an allylic position. But we have that last one, the second to last one we looked at, which was difference in electronegativity, right? So we could have a resonance structure that just looks like that. Which gives you a positive charge on the carbon there. You take electrons away from it. Negative charge on the oxygen. Again, not super stable on its own, but there's another resonance structure now we can draw, right? Because now we've got pi bond adjacent to a carbocation. Right.
So I went like straight to the last one. Would you be okay with that?
This one's definitely going to be more stable than that one. If it just says draw resonance structures, it doesn't specify how many or all. This one is actually going to be more stable than this one. Because they both still have a carbon with an incomplete valence, but this one has the positive and the negative charge further apart from each other. So going straight to here is not wrong. You're just missing one along the way, but that's going to be a pretty insignificant contributor because of how close those positives and negatives are.
I mean, I put both arrows going down, but
Yeah, as long as you draw both arrows, you're not wrong. There's going to be two possibilities here, right? Move one pi bond over, puts the positive charge in the middle. The second pi bond over puts the positive charge at the other end of the molecule. You guys hear about the new Beatles documentary that Peter Jackson from Lord of the Rings is making?
Wow.
Yeah, in end of November on Disney Plus. It's like a 2-hour episodes. It's all about making Let It Be in that rooftop concert in London. Managed to piece together the entire concert.
Wow.
I'm kind of excited. I'm not even that big of a Beatles fan. All right, so our two resonance structures for B, one of them is going to look like a bat. The other one is going to look like the inverse, or the flipped version of what we started with, right? What about C? How many can we do? We really only have 2 pairs of electrons that can contribute, right? Which means you're probably only going to have a total of 2 resonance structures. You move the negative or the lone pair from the negative charge over and make room for it. That's about it, right? You can't move the negative charge the other direction because these carbons are both sp3, right? All sigma bonds means no resonance. So, not a whole lot we can do there. Brad, do you have a question? Okay. And then how about for D? We already did one look just like that, right? You've got a lone pair in the Allylic position to a pi bond. So this is another one where technically we could draw two other resonance structures for this, but one's going to be very unstable. Because if we have a difference in electronegativity here, we could have a resonance structure that just looks like that. Now, that's going to put a positive charge on the carbon, because we broke up its octet, in between the two oxygens. So this oxygen now has a negative charge for 3 lone pairs. This carbon now has a positive charge. That's technically a valid resonance structure. That's going to be very insignificant compared to the next one, which would be if we move the lone pair over. Because now everything's got a full valence again. And then how many lone pairs on each of these oxygens in this last resonance structure? Three and one, yeah. Yes, that's another way of double checking that you've made a valid resonance structure is count the electrons that are either lone pairs or pi bonds. Here we had a total of 4 lone pairs and 1 pi bond, so we had 5 total electron pairs that could move around. Here we have 5 total electron pairs. There's all lone pairs now. And here we're back to 4 electron pairs and 1 pi bond. It's the same number of electron pairs that we're worried about. And all the sigma bonds we're basically ignoring. Just make sure you don't forget a carbon. It's really tempting. It's really easy to just lose carbons as you go through a reaction, especially. I don't know how many times I have to mark people down because they got the right reaction, but they lost the carbon along the way. It wasn't even a carbon, it was part of the reaction, which is probably why they forgot it. They just randomly they started with 6 carbons and now they have 5. Easy to do that, so pay attention to those sigma bonds still, even if they're not part of the resonance structure, because you don't want to do that. All right, when it comes to ranking these, as far as which ones are going to be most significant, I'm not going to have you put numbers to any of them. It's always going to be qualitative with these because there are too many factors to go into it, and the math is too complicated to have you actually put any sort of numbers to these. So when we're looking for what's the most stable resonance structure, the one that has the most filled octets is always going to be the most significant. Like this is, and these are in order of importance. The most important thing is, did you have any, all the octets filled? And then if you have two resonance structures where that both have all the octets filled, then you can go to some of these others. Right, and rank, so it's sort of a flow chart. So filled octets is most important. Formal charges closest to 0 is the second most important. Putting negative charges on the more electronegative elements is the third factor. And beyond that, and we'll learn some more splitting hairs when it comes to if you've got a positive charge on a carbon, tertiary versus primary versus secondary. We'll get to that in a little bit, but for now, if these first three are all identical, then we're going to say that all of the resonance structures that have those same categories are going to contribute equally. So like the ring, or like the I think it was B on the last one, where we had 3 different resonance structures that all had the same number of incomplete octets. This one versus so all 3 of those resonance structures have the same number of incomplete octets. They all have the same formal charge of 1 on a single carbon for all of these. There's no difference in the electronegativity of all these carbons. So 1, 2, and 3 are the same for all of these. So we'd say that all 3 of these contribute equally. In other words, it's about a normal average. So instead of being like 90% this and 10% that, it's a third, a third, a third. So if we are ranking them, if we're looking at some examples for each of these, so most filled octets, well, if we have this structure where we have a positive charge on a carbon, that's an incomplete octet, right? But if it's next to a lone pair, we can make another resonance structure where everything has a complete octet. The fact that everything has a complete octet means this is more stable than this one. Right? More complete octets means more stability, which means bigger contributor. And I've been prepping you for this. We've been sort of working this into the way we're talking about these this whole lecture, right? This should seem very similar to what we were talking about earlier, because it is. If we have a case where we've got a resonance structure where everything has a complete octet, and a resonance structure where you break up an octet in order to give the oxygen the negatives, this one's going to be a lot less significant. You're not going to have as much of this. And it's going to be really insignificant if you have to break up a full octet on oxygen. Right? Because oxygen's more electronegative than carbon, right? So this one, basically, we could draw a resonance structure that put a positive charge on the carbon, on the oxygen with an incomplete valence. But we're basically just going to say that we're never going to break up an octet for oxygen or nitrogen. Right? So if you have a resonance structure that looks like this, we can basically say, okay, well, yeah, it's technically a valid resonance structure, but we're going to call it insignificant. There's technically a tiny, tiny probability or a little bit of these orbitals mixed in, but it's so small as to be negligible. Keeping formal charges closest to 0. Even without breaking up any octets, if we have a lone pair from a nitrogen adjacent to a carbon-nitrogen pi bond, Then this molecule here, everything has a formal charge of 0. All the nitrogens have 3 bonds, all the carbons have 4. Everything's stable. It's a valid resonance structure, though, to move some electrons around to put a positive charge on the nitrogen and a negative charge on the other nitrogen. Just by rearranging the pi bond, right? Move the lone pair down, move the pi bond over. But because we went to, in order to do that, we go from something that has all, that has formal charges of 0 to formal charges of +1 and -1. And then if we do that again, we can actually put a +1 on the carbon, but now we're breaking up a valence to do that, right? So the most stable, the largest contributor is the one where everything's got a full valence and all the formal charges are 0. This middle one is significant because everything still has a full valence, even if we did introduce some formal charge. And the least significant is going to be the one where you actually break up carbon's octet, and you wind up with an incomplete valence there. Right, so for these types of problems, we're always just going to be ranking them. It's basically going to be according to most stable to least stable. We just reframe it in the context of largest contributor, major, minor, or insignificant. And usually I will just have you rank them like 1, 2, 3, 4. 1 is the most significant, 4 is the least.
I know it says most field offsets probably get all the atoms, but do we care about carbon most?
No, we actually care about carbon the least because carbon is less electronegative than nitrogen and oxygen. And hydrogen not having a complete octet just means that you broke the hydrogen off. Right, so out of our 4 main atoms we're used to dealing with right now, carbon is the least significant, which is why here it says minor contributor, not insignificant. We broke up an octet, but it was just a carbon octet. If you break up an oxygen octet, that's when we got to just being able to straight up say, forget about that, it doesn't matter at all. Here's another case where if we have something that has a negative charge, it can be what's called delocalized if you can move that negative charge around. So if you have a negative charge adjacent to a pi bond especially, you can wind up moving that negative down. You still have a negative charge over here, right? Because you started with a negative charge, you still have to have a negative charge. You can't get the formal charge to 0 in this case, right? Because the whole molecule has a charge. But these two are going to be significant contributors because you still are just sort of moving that negative charge back and forth. Everything still has a full octet in both of these. If you drew a resonance structure that looked like this, where you actually wound up with that's actually very similar to the one that we were drawing a second ago, where we said, okay, there's a negative charge here, and then there's adjacent lone pairs. We broke up a carbon's full valence, and we introduced more charges at the same time. That's going to be really unstable. That's not going to be a significant contributor. Right? So even though these charges still add up to the net -1, the fact that we went from everything being neutral except for one atom, and then added more negative charges here, and broke up a valence at the same time, it's not going to be a significant contributor. So same example we were just looking at, you've got this molecule with a negative charge here. If we have to look at between these two, they both have formal charges as close to 0 as possible. They both have formal or filled octets, filled valences as much as possible. Everything has a full valence. Can't get more filled valences than everything, right? When it comes, this is now we're getting into the level of sort of splitting hairs. These are going to be closer and closer to 50-50, the more that they're almost the same stability. putting a negative charge on an oxygen versus putting a negative charge on a carbon. If we have to have a negative charge, we might as well go on the more electronegative element. And so now we're getting into the realm of maybe this is like 70-30. It's not 90 to 10 or 99 to 1 anymore. It's getting closer and closer to being the same stability. Because these are your most important octets. Get your formal charges as close to 0 as possible. And then worry about negative formal charges on more electronegative elements. And again, once you can say that 1 through 3 are all the same for a particular set of resonance structures, you can say that they're all going to contribute equally. So in this case, so for carbonate, CO3 with a -2 charge, right? So carbonate looks like this. So you've got 2 oxygens that each have a -1. And you've got a carbon in the middle with full valence. The oxygen that gets the double bonds doesn't really matter. All of them basically get to take their turn. They all get to share having that pi bond. So each of these is going to be an equal contributor. The other possibility would be, well, we have an oxygen with a double bond to a carbon, right? So we could break that pi bond and turn it into a negative over here and a positive on the carbon. But we'd be introducing more formal charges if we did that, and we'd be breaking up a carbon valence to do that. So even though we technically could draw that, that's going to be an insignificant contributor. Right? Because our most significant thing is fill all the valences. And then it's fewest formal charges. And then it's about putting negative charges on the oxygens. Right, so again, these are all going to be equal. And that's going to be insignificant. So maybe it's 0.33, 0.33, 0.33, 0.01. And actually, it's probably more zeros there. When these are all equal and fairly stable, and that one's really unstable, could be more like, yeah, there's an exponential relationship between energy and equilibrium constant, right? And which also applies to orbital mixing. The more, it's probably going to be a lot more like, 1 in 10 to the 6, 1 out of a million here, and then the rest of it split evenly between the other 3 possibilities. All right, so how do we practice this? Well, if I give you resonance structures, you just rank them. So out of A, B, and C, what's most stable, what's least stable?
C is low,
C is the most stable. Why?
because everything has a full octet and there are no charges.
Good. And it can be, sometimes it's easier to find the things that are least stable first. So I started you the wrong way on that one. Because a lot of times things that are the least stable are going to look wrong, even if it takes you minutes to put your finger on why. This one has no pi bonds, has 2 formal charges, and has an incomplete octet. So this doesn't meet any of our criteria. This one's going to be the least stable. And then out of these, you can say, okay, well, this has everything is a complete octet, and this everything has a complete octet. So then it becomes, now we go to the second level of our criteria. Okay, well, this has no formal charges, and this has some formal charges. So C is going to be the most significant, be the greatest contributor. A is going to be a minor contributor. And then B, insignificant. right? So the other way I can do that, I can ask questions, and this is really testing both, can you draw the structures and rank them, is exactly that, draw them and rank them. Right, so we'll do the one on the left first. All right, so for the one on the left, we've got extra electrons, right? We don't have any incomplete valences, we have extra electrons, which tells us we're going to be pushing electrons, not pulling them into an empty spot. And the negative charge or a lone pair adjacent to a pi bond in the allylic position, you're just going to move it over and then make room. So we have 3 additional resonance structures that put the negative charge in the benzene ring and resonate it around the benzene ring. Which of these, or any of these, do any of these have a incomplete octet? No, everything's, we have extra electrons, not too few electrons, right? So no incomplete octets. Which means, so we're not worried about that. Do any of them have more formal charges than the others? No. They all have the same number of, they all have one formal charge. So what's our last criteria? Electronegativity, yeah. So which of these is going to be the most stable? Yeah. The first one's going to be the most stable because if we have to have a negative charge, it might as well be on the more electronegative element. Nitrogens are already the best at pulling, better than carbon at pulling electrons towards themselves. So this is going to be your major contributor. Is there any way of differentiating between these 3? No, they all put a negative charge in the benzene ring. It's a negative charge on the carbon for all of them. Same number of valences filled, which is all of them. Same number of formal charges for all of them. So these are all going to be equal. They're all tied for number 2. And our most significant is one we started with. We see that a lot, actually. A lot of times if you're drawing something that has multiple resonance structures, especially in a textbook or, if you look in the, in the stock room, at the structures that are drawn on the bottles for some of these, there are things that have a lot of resonance structures that are just drawn with only one resonance structure shown. That one resonance structure that you choose to draw is usually just the most significant one. The others are there, and once you've taken OChem, you understand that, or at least know about it. But we're not going to bother putting all 3 of these on the stockroom, or all 4 of these on a stockroom bottle. Yeah.
I may have missed this at some point, but does resonance give these molecules different properties?
It does. It changes how, well, one, it changes where you can have something else come in and attack it. If we had something with a positive charge in here, there's 4 different places where there's a negative charge where it could attach. So it's going to affect the products that we get when these react. But it'll also affect how stable they are on their own. Benzene's exceptionally stable because of all the resonance structures that it has. And if you try to get benzene to react with something, you have to break up those resonance structures, which makes it really, really stable, more so than other similar compounds that are similar on the face of without resonance. So it affects polarity. It affects a fair number of things, especially. It also especially helps us understand why things that on the face look unstable, why they're actually more stable than we would expect. Why, for acetate's a good example. Why is acetic acid acidic? So acetic acid looks like this. Now, there's a little bit of resonance that can happen here, right? But it's not going to be a very significant one because you're going to wind up making formal charges to do it. But if you take this hydrogen off, now all of a sudden we have something where we have to have a formal charge, but it can resonate back and forth between the 2 oxygens pretty easily, right? So this is more stable than we would normally expect, which is why acetic acid is more acidic than ethanol. If we had still the same 2 carbons, but instead of having the possibility of resonance, we just had just an OH here. On the face of it, it looks like that hydrogen should be just as easy to pull off as this hydrogen, right? It's still a hydrogen attached to an oxygen. But there's no resonance that can happen if you pull this hydrogen off. You get a negative charge stuck on this oxygen that can't do anything. Versus having a negative charge that can resonate. So it allows us to, especially when it comes to acidity, but it does allow us to explain a lot of relative properties when it comes to things like solubility and acidity. Plus, it's one of those things, it's an easy skill for them to write multiple choice questions about. And so it shows up a lot on standardized tests. If you have to take OChem to take your standardized test, to take the TEAS test or the MCAT or whatever, it's a really easy thing to write a multiple choice question for. Like, which of these is not the resonance structure of this compound? Right? And so it lends itself well to showing up in other places that way too, which is why it's one of the first things we cover. All right. We'll end there. We'll come back. So your quiz this weekend will be drawing resonance structures and ranking them. Right, so lots of stuff, the same stuff we've been covering over, shouldn't be any surprises. I'll double check, but yeah, functional groups shouldn't show up in this one. That was just to make sure that we're on the same page with class and nomenclature. And I will see everybody on Tuesday.